more people? একেবারে গণেশই তো হয়নি সবাই। So okay, we started with a little, but then it ended in the middle. So we were discussing about what is a Hilbert space, and the sequence in which is that you have some amorphous collection of elements which you call a set, and then in that set you define a group with the operation plus, and it is an additive group, that is because of this notation plus, and it's also abelian. So A plus B and B plus A is the same thing. And then in that group you define something which is called the, you define multiplication by a scalar. This scalar can be more general, like it can be an element of an arbitrary field, but for our purposes we will only take them as complex numbers. Okay. With this structure we have what is called a linear space, or also called a vector space. It's mainly in mathematics books they usually write linear space, in physics books they write vector space usually. And in that linear space we define a norm which is denoted like this with the vector here, and it's called a normed linear space, and it satisfies certain usual properties of the norm. You can think of it as the length of a vector. Then there is something called the Banach space, which are complete nonlinear spaces. And as we discussed the last day, this completeness has to be distinguished from the completeness of the basis, like these type of relations that we learn. So this runs over a full basis of orthonormal vectors in space, and I mean, this is inside a Hilbert space, of course. We haven't even gone to Hilbert spaces, but I mean, this is also called the completeness relation. We are not talking about that completeness, okay? This is a different completeness. It essentially says that there are no gaps in the space, in the sense that a sequence that wants to converge is able to converge. Yeah, the Cauchy sequences are converging. So these are these Banach spaces, and in this Banach space we define an inner product, and then we call it a Hilbert space. So there was some confusion the last day about this parallelogram. तो आज मैं रट्टा मार के आया हूँ वो वाला. So if you are inside a Hilbert space, then the parallelogram is always valid. So the law is, as you said, all of you, the last day, that it essentially says that the sum of the squares of the diagonals is equal to twice the sum of the squares of adjacent sides. Yes. So if you have this A, B, C, D, so then this AC square plus B D square is twice of A D square plus A B square. Okay. And this is the thing. In terms of vectors, it's like it's some U. So if you call this as U and this as V, so plus V square, twice of that is equal to norm of U plus V plus squared and norm of U minus V the square. Yeah, so this is the usual form of the parallelogram law. This is valid in any Hilbert space. Now if you have a Banach space in which the norm satisfies this property, then you can always define an inner product that will satisfy the usual properties of an inner product. And the inner product is defined like this. So you define the inner product between these two, or if you want to write it in terms of the quantum mechanical notation, bracket notation, it looks like this. Then you can always, and now I'm again forgetting, I think it's like this, is summation over I power k norm of x plus I power ky. I guess there's, I forgot whether the square is there or not there, find that out. And it goes from 0 to 3. Yes, so if you are in a Banach space and you know, so there are Banach spaces in which this one is not true, but suppose you have a Banach space in which this is true, then you can define this in that Banach space, and by using this property you can show that this satisfies all the properties of being an inner product.
That is a square.
Pardon? There is a square, no?
So only those Banach spaces are Hilbert space which follow this property.
Exactly. And to find out an example of a Banach space which does not follow the parallelogram law, you can take this LP spaces where if you have a vector x1, x2, xn, which is this LP spaces look like this. The norm is defined as x1 power p plus x2 power p and etc. up to and goes up to n, of course, and power 1 over p. This satisfies this parallelogram law for some specific values. I think for p equal to 2 and so on, it satisfies, but otherwise it doesn't satisfy. In general, it doesn't. So this is the Hilbert space. And now, So we will be dealing with Hilbert spaces, which are, we have already said that the field is complex numbers, and so these are called complex Hilbert spaces in the sense that the field are, you can have real numbers. We discussed about this real numbers and quaternions last day. Moreover, we will always be concerned with a specific class of complex Hilbert spaces, the so-called separable Hilbert spaces. It's a sort of a abuse of notation. This separable has is used in many things inside mathematics, and I will tell you what this means. And it has nothing to do with the separability problem that we do in quantum information. This what is very old. So by separable Hilbert space, we mean that the corresponding Hilbert space has a countable basis. Yes. So of course, every finite Hilbert space falls inside, but we are talking about infinite Hilbert spaces. In infinite Hilbert spaces, we will be concerned with only those in which the basis is countable. What do I mean by countable? The definition of countability is that, so suppose this is the basis of some Hilbert space. This is a basis of some Hilbert space H, and let the elements of this be Bi. Oh, well, this I may not be an integer, okay? I mean, if you want, you can call it B alpha. Now it's called an countable basis if there is a one-to-one connection, one-to-one onto correspondence between this and the set of integers. Can be positive integers, let's say. So say natural numbers. Then you call the basis as countable. Yeah? This is the definition of countability. So we will be concerned with only those Hilbert spaces. Those Hilbert spaces are mathematically, they have good properties, and we hope that physically they will be enough. There are troubles when you go to the position basis, and we will see when it comes. That is not, that will not fall in this category. We discussed about the Riesz theorem last day, right? The Riesz representation theorem, so it says that the set of all functionals on a Hilbert space appear only as inner products. Yes, this we discussed the last day. And then one more theorem that we will on and off use is the so-called, maybe you have already discussed it in QIC-I. We will not use it so much, but it is very useful in QIC. It's called the Hahn-Banach theorem. This Hahn-Banach theorem is true in any nonlinear space, but we will be using it only inside Hilbert spaces. And that is all about Hilbert spaces that we will discuss. If you have any question, you can tell me.
So,
Yes.
So what does it mean for a sequence to be convergent in a Hilbert space?
So when you have a Hilbert space, then this is it has a norm and by using that norm you can define a distance function, yes? So if you have two vectors x and y, then the distance between them you can define that as x minus the norm of x minus y. And this will satisfy all the properties of D being a metric. And then when you have a sequence, let's say xi, then this is convergent to a vector x, means that well, there is an epsilon delta definition, but I mean the main thing is that the limit as I goes to infinity of xi is x, but in the, this is a meaningless statement, yes, unless you know that this is what I mean. So if you want to make it more specific, more mathematically correct, then you have to say that for all epsilon greater than 0, there exists n0, natural number n0, such that for all n greater or equal to n0, this d of xi and x will be less than epsilon.
For any vector in the series.
After n0. So initially they can be far apart, but since it is convergent, if you go sufficiently far away, they will be significantly close to this. So for every number epsilon, you choose this. Once you give me this, I will tell you where to go. You make this as 0.1, I will tell you have to go to 1000. If you make it 0.01, I will take it a million. It never ends, right? So I can go far away as possible. Any other question?
So can you please repeat Riesz representation theorem?
The Riesz representation theorem. The Riesz representation theorem says, first of all, we consider here functionals. Functional is just a name, is just a function, but it is defined from the Hilbert space to complex numbers. Yes? These functions are the functionals, just a name. But now, if this is a Hilbert space, then you can show this Riesz representation theorem tells us is that this function is such a functional always looks like an inner product. So, so what does it mean? This means that this f of these elements of this Hilbert space are the kets. So you have some x. Now this will always belong to C. Yes? This is what we already said. We are considering only those functions. So this is a complex number. Now, what the Riesz representation theorem says that for all such f, for all such f, if there exists a vector, an element y in H such that this f of x is yx. So instead of writing this, you can simply write this. Yes, so the function essentially does this. Yes. So this is the beauty of the Dirac notation. Yes, it automatically, so the Dirac notation automatically uses the Riesz representation theorem.
So is this only for linear functions?
It's for linear functions. Yes, sorry, I didn't mention this. This is a linear function. So I'm forgetting forgetting whether continuity is needed. This I don't remember. Yeah, certainly is linear. And so if one can have for antilinear function, this won't hold. This is a linear operation. I don't remember whether continuity is needed here. This you have to check. Yeah, sorry, this was only for linear functional, and this continuity I don't remember. Any other question?
What is the continuity?
Pardon?
Continuity as in?
Continuity as in the if you change the vector a little, we already have a metric, so there is a meaning of changing the vector a little. You go to a vector that is close by in terms of the distance, then the complex number will change a little. There is again an epsilon delta definition for it. Anything else?
So are we doing that Han-Banach theorem?
No? You want to do that?
Sure.
So the Han-Banach theorem, again let me say it, it's actually a terribly useful theorem for quantum information. There are laboratories dedicated to it in quantum information. Okay, it's used as an entanglement witness. But the main theorem is very easy to state. The proof is maybe not so easy. So it says that suppose the theorem is true for all non-linear spaces. I have a dream of sometime doing some work because I somehow feel that if you have a Hilbert space, then maybe something more is true. Because what we use currently in quantum information is only true for non-linear spaces. Well, the Hilbert space has more structure, but it does not give you anything more. This I am very surprised, but maybe I don't, simply my ignorance, I don't know. But let me state it just for the Hilbert space. So inside a Hilbert space, let us consider a set. Some set, so this is this blackboard or blue board is the Hilbert space. And this is the space, some set inside it. The set is such that it is convex. Yes? In the sense that if you add two vectors, it will remains inside it. Then you take something that is outside this space. So we take some x that is outside. Then you further assume that this cannot come infinitesimally close to the set. What does it mean? It only means that this set is closed. If a set is open, then you can have someone outside but infinitesimally close to it. Because what I want is to build a barrier, build a wall between these two, this one and this one. And now it's an open set, that is not possible because this you can have, I build the wall, well then I find, I will build the wall outside this set, and then I will find that there are vectors that are on this side. So this is the problem. So I take a set that is convex and closed. Why is closedness needed? Closed set needed? Because I don't want this to come infinitesimally close. Why is convex needed? Is because I don't want situation like this where this vector is like this and I won't be able to build a straight wall. I'll tell you what a straight wall is. I can of course build a bent wall, but straight walls are useful experimentally. There's a meaning to that. I'll come to that. So once these two things are satisfied, I'll be able to build a wall like this that will distinguish between this set and this set. That will say that this is on the other side and all of these are on this side. Now if this one satisfies a specific property, This one will, so this will experimentally tell us, I have some way, suppose, to experimentally set this up. I will see that this is on one side and this is on the other. It will be some part will be negative and some part will be positive. This is only sufficient condition, not a necessary one, because you see that there are points here that are also not inside this. But then I can build another wall like this. Better still is to build a wall that is as close as possible to the wall, and even touching the wall, touching the set. Because then I will be able to detect more states. I will still lose some. This is the broad thing of Hanumanak theorem. This can be made more mathematical, of course. To think it in the language of quantum information, you can think it as the set of separable states. If the separable states are convex as well as closed.
Is it always? A set of separable states are always closed and convex?
Not a separable state. The set of all separable states is closed and convex. Our set is not. We are interested to find out whether this state is entangled. So we go to the Hilbert space of mixed states, and then if I have all my separable states here, then I will be, if I am able to build a wall like this, then I will be able to witness the entanglement of this. So this wall is actually called an entanglement witness.
So the theorem is also used to show that given any something outside the convex set, you can always find this wall.
The theorem not only says that, it even gives you the wall. It is a constructive one.
No, not exactly.
You can even say that there is a functional and what the functional is. You can construct the functional by using the theorem.
Then what is the trouble in constructing a possible every witness?
No, it's only when
Yeah.
you have the function on the inside.
Pardon?
If you already know the functional on the operation of the functional on the convex closed set, then you can determine what the action is outside.
Yeah, no. The point is that for every convex closed set and every pair of these things, you can build a wall. But the trouble is, in experiments, you don't know this. And we don't even know this set properly. The structure of this set is also not properly known. So otherwise, you would have solved the separability problem. The separability problem is not solved. So the entanglement witness does not solve the separability problem, but it gives a very good experimental tool. Although you don't know what is the state that you have created, but you have some information. Otherwise, you know something about your apparatus, there may be some noise. So you know it's in this region. So you build the walls so that you are maximally away from that region.
So, and this representation is irrespective of the dimensions here?
Yeah, it's true in all dimensions. So that is also a very useful thing, because this typical criterion for entanglements are dimension specific. This one is arbitrary dimension. People have considered also nonlinear witnesses. So you can bend this one a little so that you get more states. And there's something called the detection loophole, and bending it, you can fight the detection loophole better.
So why it has to be straight?
No reason. It's mathematically easier and
Like it's by
even
definition.
experimentally
It's by
easier.
the definition, no?
Pardon?
We take some trace of some operators.
Exactly. So the way we define it to prove the Hanumanak theorem is by using functionals, the linear functionals. So typically what it looks like this is So this is how a weakness looks like. So this is some operator on the Hilbert space, and this trace is on the Hilbert space, and this is where either this one or anyone from here should reside. And then this one is, let's say, you can choose whatever number. 0 is an arbitrary thing actually. This is greater than 0 for all sigma belonging to the set of separable states, and there is at least one entangled row for which it is strictly less than 0. Then you call either this, actually W is most of the time called an entangled witness, but you realize that is actually trace of W, this is the witness. And since this W is an operator on the Hilbert space, you can write it down as a sum over operators. So this W can be written as AI tensor BI, where this AI and BI are operators on the local spaces. So this operator can be found out, and this is a linear operator. So this trace of W rho is summation over I trace of AI tensor BI rho. So you can implement this AI and BI measurements locally, find this out, and then on paper find out the sum, and you find out this. You already know by doing mathematics that this is true, and you by experiment you get a number that is negative, you are sure that your experiment is creating an entangled state. So now the question of course is how to, so it's experimentally easier if you can, because this decomposition is not unique. So it will become experimentally easier if you can write it down with the minimal decomposition, minimal number of terms. So in some cases that minimal decomposition is known, but it is not a solved problem in general.
In general, as in arbitrary dimension.
So this I don't know. I think in 2×2 it is solved. It's Maciek Levenstein and Anna Sanpera, I think, and some many Tarach, Vidal, many people they have worked on this. I don't know who has solved this. I forgot. Any else?
The Riesz representation theorem will require continuity because we can use triangle inequality.
Mm-hmm.
So if we are saying that a functional can be written as a another product,
Mm-hmm.
then say that is y. Then y of x, x in a product
Mm-hmm.
minus y x plus epsilon in a product will always be less than norm of yx in a product minus norm of absolute value of yx in a product minus absolute value of yx plus epsilon in a product. And this can be yx in a product can be written as to be equal to less than, will be less than the Cauchy-Schwarz inequality. We can use Cauchy-Schwarz inequality to say that yx in a product is less than y norm x norm, and similarly for yx plus epsilon. So
That is true. You are assuming that it can be written as an inner product and then proving it is continuous. Yeah, that is okay. But whether I am asking the opposite.
All the functionals which are continuous can only be written as
Because the
yeah,
right hand side is already assuming continuity. The inner product.
I'll have to see this. Why is the right hand side assuming continuity? Because you mean that the vectors themselves will be continuous. Maybe. I'll have to check this carefully. Anything else? Yeah. So this was of course just a primer, and So we sort of discussed about Hilbert spaces. Why did we discuss? Because for every quantum system, we plan to connect it to a Hilbert space. Yes. So if you have a single quantum system, then for every such system, whatever that slippery thing is, we say that there is a Hilbert space corresponding to that system. Moreover, for every Hilbert space, we say that there will be some system that will represent a physical, that will be there in nature. And now when I say it's a Hilbert space, it's a complex separable Hilbert space. Now every Hilbert space has a dimension. Well, even a linear space has a dimension. And this dimension will be the number of degrees of freedom of this Hilbert space. Yes? So this is a system. For every system there is a Hilbert space, and the number of degrees of freedom will be the dimension of that Hilbert space. We don't define, just like we didn't define what is the system, we will not define what is the degree of freedom, we will assume that we know it. Yes. It is somehow we know it by experience. It's like a point in mathematics, we don't define it. Yes, and so the system has a state, a situation. A situation in this system will be a state here, and by a state we mean it's also called a density matrix. And a density matrix is a Hermitian positive unit trace operator on this Hilbert space H. Yeah. So again, this on H, the word means that the operator rho is from H to H. Yes, this is the usual meaning of this word on. Yes. So in most books, positive means Hermitian. Okay. So sometimes this Hermitian is left out. They just say positive. In some books they write both. So it Hermitian, all these words you know. Yes, Hermitian means rho dagger is rho. Positive means the eigenvalues are positive, and unit trace means the sum of the eigenvalues are 1. Yes. By the way, I don't know whether I mentioned on the last day, there is something called the spectral theorem that we will be using, which says that if you have an operator n which is on a Hilbert space H, which is normal, which means that n dagger n is n dagger. So it includes unitary operators as well as Hermitian operators. Then you can write that n as summation over, this summation can be partly integral, okay, in the sense that there can be some part that is continuous. The summation over lambda I, these lambda I are the eigenvalues of n. This I runs over an eigenbasis of, is the eigenbasis of n, and it's a basis of this H. orthonormal basis. Page. But in some cases, some of the lambda is maybe missing in the sense they are 0. In that case, this will not be a basis. It will be an incomplete basis, yes? Is the thing. But you can always include zeros to make it into a complete basis. And some of these lambda i's can be equal, and that will be very important for us. Some of these, some may be 0, some may be equal to some others. Yes, so this is the spectral theorem. So in this case, Hermitian means that the eigenvalues are real if you just use this theorem. Positivity means that these lambda i's are positive. Unit trace means that the lambda is sum up to 1. So it essentially means for states, the eigenvalues form a probability distribution. Yes?
And why is it essential for a density matrix to be Hermitian? I can understand why operators have to be Hermitian because the physical values stand out to be real. Why is it necessary for a state to be Hermitian?
To say it, well, the short answer is postulate, and the long answer is
Real eigenvalues.
pardon?
You need all the observables to be real. That's in that spectral decomposition, we need a real coefficient with all the basis vectors.
Spectral decomposition for is possible also for unitary operators. In that case, these are not real.
Yeah, but we need real because we connect them to classical observable.
Exactly. So there are theories where you can build up a theory of quantum mechanics where the observables are not Hermitian; they are unitary operators. People have done that. So this having real numbers as observables are real numbers as things that we get from experiments is just a convention. It doesn't have any mathematical basis, but it is useful and historically done like that. So here I would say is because we want to think of this rho, because see, once you write it like this has a spectral decomposition. So I can write it as some psi I, where these are orthonormal basis and these are probabilities. And then this gives you a way to prepare the state rho by mixing these rho i's, psi i's. What I said is only partially correct because I can create some rho 1, let's say, that is a mixture of say 0, 0 and plus plus. I can actually mix such states. You can create a state like this. This to a non-orthogonal states. But even this is not in spectral decomposition. This will have a spectral decomposition, but in some other basis.
So, but this does not form basis, these two combined.
It forms a non-orthogonal basis. It's not an orthogonal basis.
Forms a non-orthogonal
Non-orthogonal
basis. We can make that orthonormal by
You just find out the eigenvalues and eigenvectors of this, and then put the values here and eigenvectors here.
Sir, I didn't get it, sir. Can you please?
Yeah, so you can write it, right? So this looks, so you have to choose a basis. Suppose you choose the 0, 1 basis. Then this is half, and so it's 1, 0, 0, 0, yes? And this is where it's 1, 1, 1, 1, yes? And then you add these, and you get. There's one more half, no? There's 1 by root 2 there. So just a 4 here. Yes. So now you can write this. This is half, and this is 1/4. So it is 3/4, and this one is 1/4, and this one is 1/4. This one is 1/4. Yes, this is the matrix. This is written in this basis. You have to always remember when you write a matrix. You remember in which basis you are writing. So this is in this basis. Now you diagonalize it. You find the eigenvalues and the eigenvectors. Suppose they are some, let's say lambda 1, and lambda 2. It will always have two eigenvalues and eigenvectors.
Yes.
You find them and suppose these are these. Then you can write this as lambda 1 plus lambda 2. This will be, these two will form an orthonormal basis. This on the other hand forms an non-orthogonal basis.
Do you have to find out the orthonormal basis by decomposition, or can I say that 0 and 1 form orthonormal basis as well?
0 and this was just a choice. This I could have written it in the plus minus basis also. I can write the matrix in any basis. This was my choice that I chose those bases. But once you choose it, you write this, you find out the eigenvalues and eigenvectors. Since I have chosen this basis, you will get these lambdas and lambda 1 and lambda 2 written in this basis. The vectors will be given in this basis. Had you chosen the plus minus basis, you will get the same vectors you will get in this plus minus basis. But now they will be orthonormal.
So what is the physical significance of eigenvalues of density matrix?
Physical significance in the sense that, so suppose these are the eigenvalues and eigenvectors, and as I told you, these are two positive numbers that add up to 1, well, can be 0 sometimes. So this tells you that the preparation of this rho 1 can be done by mixing these two vectors. And these two vectors this time are orthogonal. So you can think of them as classical, blue flower and pink flower. So this we must remember all the while that distinguishable situations in the physical world is represented in the mathematical representation as orthogonal states, orthogonal vectors, or orthogonal density matrices. But the point in quantum mechanics is that this gives you a method of mixing two This gives you a method of mixing two classical vectors. Classical in the sense two distinguishable vectors, two distinguishable situations. Whereas here, these two are indistinguishable situations, you can still mix them. You can make it more complicated, and those complicated situations also exist. In the sense that you can have a situation where you are mixing with 1/4 probability you take the 0, and with 1/4 probability you take the state plus, and with what is left, half probability you take minus. This is not even a basis. This is a linearly dependent set. But you can think of a situation where you are mixing these three. Again, in that case, you can do this exercise and find out these things. Again, you will only have two. The orthonormal basis has only two elements because we are considering a two-dimensional space. And then you can think of mixing it in that way.
So after finding the eigenvectors of that one,
Mm-hmm.
I'll have eigenvalues. So
As
I
well as
cannot say it
eigenvectors.
is related to probability.
Pardon?
Can I say that is related to probability, the eigenvalue?
Exactly, this is what I'm saying. That once you find out the eigenvalues and eigenvectors, you have two numbers and these two vectors, these two numbers are positive or maybe 0 and they add up to 1, and these two vectors are orthogonal. Orthogonal vectors represent distinguishable situations, and these are probabilities. So you are in a situation, rho 1, which can be obtained by mixing these two classically distinguishable situations, classical situations, mixed with these probabilities. Fine. So yes, we come back to our thing. So we have a system corresponding to it. There is a Hilbert space. That Hilbert space has a dimension, and that dimension comes from something that we call the degree of freedom. Every situation is a density matrix which has these properties, and any density matrix that you write on paper in that Hilbert space, which is Hermitian positive unit trace, you assume that we can create such a situation in this system. Yeah? We assume that all density matrices are valid. The experimenter can have a difficult time in actually creating them, but we assume that is valid, yes? This thing is the reason that we get our salaries. We survive by this other implication. And happily, there has not been a case where we can safely say that this density matrix cannot be created. There are controversies with the Schrodinger cats and so on, but otherwise we strongly believe that all density matrices can be created. Distinguishable situations, as I said, correspond to orthogonal density matrices. Yes, orthogonal. So that means that rho 1, rho 2 is 0. And that is all what we would like to call as, I mean, this is not standard terminology, you can call it quantum statics. So this is the static description of a quantum system. We haven't yet done anything with it. Yeah? We haven't measured, we haven't evolved. This is just the state that I have. There are people who do research only in this area, including many people in our group. And classically, this you wouldn't even consider doing research in this, but in quantum mechanics, people do research already here. And then, of course, once we have statics, we consider quantum dynamics. This is a standard term, and it's actually a very broad subject, but it's easily stated in the sense that when you have a system that goes from one situation to the other, it will go from some rho 1 to some rho 2, and the postulate of quantum mechanics is that this always happens via a unitary operator. So this rho 1, rho 2, u and I are all defined on this Hilbert space. This is a unitary operator. These two are density matrices with these properties, and this is an identity operator. So it doesn't typically look like the Schrodinger equation, but it is actually the Schrodinger equation. So this is, I mean, this is deceptively simple, but people write entire books on quantum dynamics, okay? We will see some examples of that. So until now we have dealt with the case where how to describe the system and how to describe its evolution. But all this is of course not provable unless we do a measurement. The information about the rows and the U's comes only via some measurement. And even here, so this quantum statics and the quantum measurement essentially does not have any parallel in the classical world. And I mean, it does have, but it's considered to be trivial for the classical case. So what is the measurement in the quantum system? It's that you have, we consider it some sort of a black box which has some outputs and it has some input. The input you describe as rho and the outputs as some projectors P1, P2, etc. These projectors are orthogonal to each other because you actually distinguish, you see that it came out through this or this or this. And this is what we say, that situations which are distinguishable should be orthogonal. So this is from there. So quantum measurement, postulate 1 of quantum measurement is that outcomes are arbitrary. I will change this postulate in a minute. So in a given situation, I don't know which one will click. This is a postulate. Number 2, the probability that the ith one will click is given by this. It's called the bond rule. Now, if you find out from the bond rule that some, let's say P29 is 0, that will never appear. So outcomes are arbitrary unless having 0 or unit probability. Yes. If you find out that you have done a measurement in which you always have one clicking, the probability is 1, then you don't have any arbitrariness. Or if there are only there are 3 outcomes, and one of them you already know is to be 0, so it will. We are considering ideal setups. In a realistic setup, even the probability is 0, it sometimes there is called dark counts and all. Fine. So these P1, P2, P3, these are projectors, and any one of them, because the projector is also Hermitian, so you can show by using the spectral theorem essentially that you can write it as a sum of orthogonal projectors, which has unit rank. So you can write it as, let's say, A1 plus A2 like this. Any projector can be written like this. So the ith projector will have this. So if it, let's say, suppose it stops here, then this Pi, we call it as rank 2, is the rank 2 projector. So typically in standard textbooks of quantum mechanics, these, is it mine? প্যান্ট্রিতে এসছো? 12:30 ক্লাস শেষ হবে। তো আচ্ছা, আমি 12:30 ক্লাস শেষ করে যাচ্ছি। ঠিক আছে, প্যান্ট্রিতে। সরি। So, as I was saying, that typically in textbooks, people consider these textbooks consider these operators as rank 1 projectors, and then there's only one term in each, and then this thing looks like some A rho A. This thing will become like this, and if this rho on top of it is a pure state, then it will look like this. Depending on how many times we have studied quantum mechanics, you go from here to here to here. So this is where the so by the way, so why are we interested in these higher rank projectors? You will see that there are several problems in quantum information, in particular state distinguishing problems, where doing higher rank measurement is useful. If you do low rank measurement, let's say the rank 1 measurement, because you see what you are doing, you will see why that is so in a minute.
How does one implement this higher rank measurement experimentally?
Well, to be sure, I don't even know how to implement the rank 1 measurement. Let me see if I can remember anything about it. I don't know.
Is there a reverse process of a beam splitter?
Pardon?
Is there the reverse process of a beam splitter?
That is not
No. One has to, and for a rank 2 measurement, one has to consider at least a 3 dimension. Yeah, I mean, in 2 dimensions there are only rank 1. I mean, projection measurement is only rank 1. But so you go to spin 1, and I don't even know how a spin 1 Stern-Gerlach looks like. So this is some sort of a Stern-Gerlach with many outcomes. I don't know. It's good to say I don't know.
For rank 1, you can, like photon measurements like polarization, you can do that, right? Rank 1.
I can give you I don't know how to do the experiment. Yeah, I mean, I can give you lots of examples. So you consider the Fock states. So this is the Fock basis for a photon, and then I mean for a mode, and then you say you consider this measurement. And so on. This is the rank 2 measurement, but I have no idea how to do it actually. So this is a rank 1 operator. These are all rank 2 operators. This very much falls under this category, but I don't know actually. I think this actually, I have heard people say these experiments that this I think will be very hard. But there are measurements which are rank 2 and they have been done. People have done. So it's not always hard to do, implement. But I don't know how to do it.
So in general, in quantum optics, they measure some states, right? So that measurement itself is kind of projectile. It's kind of like using a projectile.
Yeah, exactly. So this is what happens inside the black box. Yeah, I mean the quantum measurement problem is not solved. I mean, so a lot of people have tried to understand this going to there via a unitary operator with some tweakings. These have not been successful as yet. I mean, it's not completely successful, let's say. Zurek, for example, is one who has given a theory decoherence, Ein selection theory. There are many people who have that Girardi-Rimini-Weber theory is another theory. There are many people who have many theories on measurement, but none of them are completely successful. Okay, we come back to the quantum measurement problem. I mean, in standard quantum mechanics usually stops here by saying that this is quantum measurement. We in QIC and in other areas, we also want what is the state after it comes, after what is it that comes out. And then we assume that the state that comes out is some rho I, and it is pi rho pi. It's not normalized. You have to normalize it by trace of this thing. But trace of this thing is you can bring this thing on this side, right? And there is the p square, but p square is p. This is, you have done all this in terms of vectors, of course, and maybe also in this language, I don't know. But certainly in terms of vectors, you have done this, where you assume that, let's say, is a horizontal polarization and a vertical polarization in the superposition, and you measure the horizontal vertical polarizations. And this is the input, and the probability that this clicks is mod alpha square, and probability that this clicks is mod beta square. So those mod alpha square, mod beta square are exactly these things, or these things. And if you do this exercise on this, you will see that you will get some mod alpha square HH, and then you have to divide by the trace, and which is this. So what we are trying to say is that after you do this experiment, you get this state with this probability. In the optics experiment, this is very difficult to do, because the photon will actually be absorbed in the detector. But in some cases, this is possible to do.
Considering that bond rule,
Mhm.
is with the context of explaining a bit of Riesz's theorem, whether that takes that if density matrix is written that from then bond rule will be this, or it derives that, or
First of all, I forgot the Gleason's theorem. So the Gleason's theorem tries to give a meaning to the bond rule. I've forgotten this connection. Sorry. Tell you next day. I have to read it out. But thank you for that. There is a connection of Gleason's theorem in bond rule.
it derives that, or
Well, derivation is not the correct word. I mean, it gives a intuitive meaning to it. You can't derive. More questions, comments, mistakes? Okay. So, of course, I wrote single quantum system with the intention of writing two quantum systems. I mean, this will be the end, okay? I mean, I will not go 3, 4, 5, 6. So first of all, if I have two Hilbert spaces, then the tensor product of them is another Hilbert space. Okay? This is a mathematical fact. I'm assuming that you know what is the tensor product of two vectors. And you take an arbitrary vector from this Hilbert space, an arbitrary vector from there. You take the tensor product of them, and you take a linear superposition of all such products. The linear space still, and that's again a Hilbert space. This you can show. Why are we thinking about this? Because we say that if we have two physical systems, corresponding to them we have two Hilbert spaces, but when we say that I consider the two systems as a single entity, then the corresponding Hilbert space is the tensor product of the individual spaces. This apparently, I mean, physicists usually consider this as trivial statement. But there are some mathematical subtleties to it. I am told, I don't know it for sure, that it is not clear whether this is the only option to take. There are many other ways you can combine Hilbert spaces and all. But whatever it is, it's good to think of it as a postulate.
Which will
Be
also
careful.
be Hilbert space.
Pardon?
Other combinations will also be Hilbert space.
Yes, that is fine. So that is also believable, but they will have other problems in those combinations, linearity and all these type of things. I don't know the details. I heard it from people. So for us, if I have two physical systems, I know the individual Hilbert spaces. When I take the whole thing as a single entity, we will consider the tensor product Hilbert space as the Hilbert space corresponding to that. And as you can check that the dimensions get multiplied. This is actually a very important fact for us and for many others. So for example, if I have, let's say, a spin-off system, spin-off an electron, I can represent it in C2, so this is a complex two-dimensional Hilbert space. But if I have two spin-off particles, I have this. Now it's important to say that two physical systems, two distinguishable. We already used the word distinguishable before, but that was for situations in a single system. Here we are calling distinguishable systems. Yes, we are not in identical systems. An identical system, this postulate changes. We will not go into identical systems very much. The quantum information theory is sort of slippery once you go into identical systems, and it's not a very well established way to define properties in those quantum information properties in those systems.
So it is distinguishable and non-interacting systems.
Not necessarily non-interacting. It can interact. But I always know their identities. I know this and that. I can name them. In that case, this postulate is true. Otherwise, if these are bosons of fermions, these will change, depending on whether you give a symmetric or antisymmetric space and so on. Quantum mechanics of non-distinguishable systems is well known. It's the quantum information of identical systems that is not very well established. So then for two spin-off particles which are distinguishable, we will represent it like this. And the corresponding Hilbert space will look like this. It's a four-dimensional space. So now, if so this is the thing. So this will actually be some CD1 tensor CD2. This is a D1 dimensional complex Hilbert space and D2 dimensional complex Hilbert space. And then a state in this space, a situation will be situation in this joint physical system will be a state on this joint Hilbert space, and it will be a rho that will be defined on this. Yes. If state rho 1 goes to rho 2, then it will be U rho 1 rho 2 U rho 1 U dagger, where this U is unitary. But now this rho 1, rho 2 and U are operators on this bigger Hilbert space. So this was the statics, dynamics, and then one has to measurement. A quantum measurement, now one has to consider a set of projectors on this Hilbert space. Yes. So these PIs are now on the same thing. And so we had this summation PI as the identity, and this identity was previously on a single space. Now this identity is on this bigger space. Yes.
Sir, if these two systems are interacting, can I say that they are always separable? Non-interacting. If they are not interacting, can I say that they are always separable? I mean, if they are interacting, can I separate both of them? If they are interacting.
By separable, you mean not entangled. That separable you are talking about, right? Yeah. Yeah. So by when two states, two systems are non-interacting, then the only thing that you can do is an operation U1 tensor U2. I will change this statement later on, but let us assume like this. So this is on this Hilbert space, this is on the other, and then you begin with some row that is on the bigger thing, and you have U1 dagger tensor U2 dagger. And this thing, if this state did not have any entanglement to begin with, it will not have. But if it already had some entanglement to begin with, it will have the same amount later on. So these are local unitary transformations, which is essentially a local change of basis. So the two observers at the two laboratories have changed their axis. They are looking at it, they have tilted their axis. So essentially nothing happens to them. To the global properties, nothing changes. The local magnetizations can change, because what you used to call an X magnetization now is actually the Z magnetization. Those things will change, but the correlations will not change. Neither the classical correlation nor the quantum correlations, but the classical correlations can change in the sense that what you used to call as the XX correlation now has become ZZ correlation. In that sense, it can change. But we haven't gone there. I mean, this is not the only local operation that you can do. There's this LOCC thing that one can do. In that case, the entanglement cannot grow but can go down. This will come later.
That is local measurement. LOCC.
One can have measurement, one can have other things like loss of a part of a system.
So if they are
No, this is not true. If they are interacting, they may get entangled. So this is for two systems. Of course, one can now have an array of quantum systems, and then you will have an array of Hilbert spaces, and things will go through just like before. Of course, there will be more and more troubles in understanding the systems as you go to bigger and bigger spaces. So, for example, as you will see that the entanglement of two systems is fairly well understood, but beginning from 3 or higher, the meaning of entanglement gets slippery. Even to define what is entanglement, well, what is entanglement is okay, but what it can do, it becomes much more complicated. So, an example where you have an array of quantum systems is, for example, if you have a condensed matter system or a cold gas system, they typically consider these arrays of systems. It can be a one-dimensional array or two-dimensional array, or three-dimensional sometimes.
It is 3 dimensions.
Pardon?
You can't do 3 dimensions.
Almost never. You consider. So, I mean, the idea of these first few classes is sort of giving a review of what we will need in the later part of the course. So, these are some things, and the other things I will just write the names and tell me if you want to discuss them, then I will discuss, otherwise we will carry on. We'll finally go into these algorithms. So the purpose of these first few days is to see whether we are on the, so set the notation essentially, and we are on the same platform. So this is very important, the quantum no cloning theorem. So I am guessing everybody knows it. So which just says that if I have a state, it can be given in terms of mixed states, but let me give it in terms of pure states. So what I want is something like this, that I have, so you can think of it as a Xerox machine, where I have this input, and this is the blank paper, and this is the machine, and at the end I want my book back, the blank in the same state as the book, and the machine may be heated up a little, and that heating up may depend on which paper we were Xeroxing. And you can show that for arbitrary psi this is not. It is possible only if these psi's come from orthogonal basis, orthogonal set. There is quantum, no, this is not a standard, this is a standard terminology. There is what one can call a no leaking theorem. You cannot leak out information. What does it mean? It is a weaker version of the same thing. Suppose I want from here, I want to keep this state the same, and so let's not even have a machine. I mean, let us have the entire environment. So it contains the blank state, the machine, and everything else in the universe. This, I want some E that has a little bit of that information. It may not be an exact copy. So this E psi may not be of this form. It can be anything, but with different psi, it is a little bit different. This is not possible unless this is from orthogonal set. So cloning is actually a very drastic form of leaking. So even smaller versions, a little bit of leaking. So if you keep your initial thing intact, your environment will have no information about your system. This is sort of you can think of this as an atomic version of the information disturbance theorem that are in early days of quantum mechanics. People thought of the Heisenberg and these people that they were talking about that if you take out information from the system will be disturbed. So this is sort of a very atomic version of that. So when I began my PhD in Bose Institute, well, I first began in Bose Institute, and then I was very happy because I derived this. And then I found that people have these type of theorems in appendixes of their papers. So this is a statement for pure states. We'll go back to the no-cloning theorem. There is so if you consider mixed states, then there is a very important theorem that says that if you have non-commuting mixed states, if you have, so like here, if you have two states, psi 1 and psi 2, if this is not equal to 0, they are non-orthogonal, and then you cannot do this. Non-orthogonal states, pure states, the projectors of them are of course non-commuting. They don't commute. So if you take the commutator of this is of course not equal to 0, this implies this. But we go to mixed states. So we have two states, rho 1 and rho 2, two situations. The representations of them are rho 1 and rho 2, and we assume that rho 1 and rho 2 don't commute. If you have such a situation where you have a system which you know is either rho 1 or rho 2, but you don't know which, and you know that they are not commuting, then you can show that they cannot be broadcast. This is a new word. We'll define what that means. So I have a system that is like this, and I take a blank state, some 0, it can be mixed also. So this is our system, blank machine. The blank state is of course the same for both. I don't change my blank paper in the Xerox machine depending on which page I am Xeroxing, yes. And the machine also is the same initially. I want it to go via a quantum evolution to some state rho 1 SBM and rho 2 SBM such that trace of rho 1 SBM, if you trace out the machine and the blank state, is equal to rho 1 of S And if I trace out S and M from row 1, I get this row 1 in the blank. Now, I want to get this for both 1 and 2. So, well, I is 1 or 2. So, you see the point? It's very similar to what we wanted here, but it is in terms of mixed states. And you can show that this thing can only happen if these two are commuting. Otherwise, it won't happen. This thing is called broadcasting. If you can do this, then you say that these two states can be broadcast. Why do we have a new name? Why don't we call it cloning? Because there's a different thing in the mixed states that can happen, that we call cloning. If we trace out the M from row I as BM, then if we get row I S tensor row I B, in that case we call it cloning. In this case we call it broadcasting. See the difference? In this case, there are correlations allowed between the S and the B. In this case, there are no correlations between S and B. It's in a product state. In that case, you call it cloning. And this can be done only when row 1 and row 2 are orthogonal. Row 1, row 2 is 0. Whereas in this case, you can do it when they are commuting.
So why is this called cloning?
Because you are actually cloning, yes. So at the end, you get two copies of the same state.
So that is rho I B is also rho I S.
I mean, this is the name of the system.
But
The state is this rho I. I mean, here I am writing the B downstairs, here upstairs. So I will not go into the proof of this. The proof is actually very easy. Well, easy. I mean, now it is easy. Initially, the paper was very important. It was by Barnum and others. Forgot the date. It's a PRL paper. Forgot the date. Okay, 1909, I would guess. And the title of the paper is exactly this.
So this arrow represents a unitary process.
Pardon?
This is for we are saying that using unitary processes we cannot.
Exactly. So this we have already assumed at the beginning that the only processes that are allowed are unitary. So maybe stop here.
Sir, when you said, so if row 1 and row 2 are commuting, are they not orthogonal by definition?
No. Let me give you an example. Take a state half, let's say 1/3, 0, 0 plus 2/3, 1, 1, and 2/5, 0, 0 plus 3/5, 1. They are commuting, they are not orthogonal. You write them in the same basis. That's the thing. Now you know why you can clone it, no? You can broadcast it. So why is broadcasting considered to be something So why not broadcasting is considered important? Because you see, these are the states that can be broadcast. And these you can think of them as in classical terms. Because they are mixtures in the same single basis. So you can think of them as blue flowers and pink flowers in this probability and blue flowers and pink flowers in a different probability. And those can be broadcast. So, but they can't be brought in this form. So what you can do is, you can bring them, irrespective of their probabilities, into, so this will go to 1/3 0 0 plus 2/3 1 1 1 1, and this one will go to 2/5 like this. This is not equal to 1/3 0 0 plus 2/3 1 1 tens at 2. It is not the same, or for this case. But this we understand classically, this happens classically as well. These are just correlated things. If you measure on one of the parts, so you have two blue flowers and two pink flowers, and you pick it and put it in one of your pockets and go to Delhi, and you keep one in your office. You take out one flower in Delhi, you realize and you find out that this is a pink flower, and you know that the one in your office is also pink. It has no option of going to the other one. This we understand classically. This is what it happens. So that is what is defined as broadcasting.
So is this a generalization of no leaking theorem?
Pardon?
Is this a generalization of no leaking theorem?
No leaking. Well, I would say the no cloning theorem. Generalization of the no cloning theorem. Not the leaking, I would
No
say.
leaking is even more stronger.
Pardon?
No leaking theorem is even more stronger.
Yeah, people. I mean, that is true. By looking at it, it looks very very more stronger. People consider them sort of on an equal footing. I mean, they don't even distinguish. Yeah, they are different. But as you go on, you see that they are used in sort of the same. And the proofs are like exactly the same. But you are right. This is more general than this, more powerful than this.
It seems that the reason we cannot broadcast to different states
Mhm.
when they are not commuting
Mhm.
is that if they are not commuting, they don't have a common eigenbasis.
Exactly.
So
So that is the
some
definition of
yeah.
commuting, yes?
So some eigenvector, if we take a projection of some eigenvector in row 1,
Uh-huh.
it has a finite component of common of projection on eigenvector of row 2, some eigenvector of row 2.
That is true.
So that seems similar to what happens in no cloning theorem.
Exactly. So it's. I mean, this is just a name. I mean, people consider the broadcasting as a generalization of the cloning, but to see that what happens for orthogonality, you can see this. Just a name. It is true, as you say, that people usually consider the broadcasting as a generalization of the no cloning for pure states. But the only thing is that here, because they are pure, because if a state is pure, then it has no option of having correlations. So, whereas here, if you have a mixed state, one can have correlations, even classical. Fine?
Sir?
Yes.
My question is more related. What, in the definition of the Hilbert space, when we constructed from a vector space to Banach space to Hilbert space, where did we allow this concept of an outer product? Or why is this?
Outer product, I
Um,
mean the.
Yes,
Get-
yeah, that. Yeah,
This one.
yeah.
Oh no, this is just a notation. I mean, this just means this is an operator. So if you have an operator, a vector A, then you can define something like this. The meaning of it is that if you have some vector B, then it will be taken to A. It will project onto A and it will be multiplied by this number. This is the operator, this is this operator. So this is just a number. So this is a projector. So it happens that the Dirac language is like that this takes this to this. So it takes this to this. This is what you wanted. You wanted every vector, unless it is orthogonal, to be taken to a chosen vector. And it happens that in the Dirac language, this is to be done like this.
So my point
And
of
people do it like, I mean, if you want to normalize it, you have to divide it by this number. If you don't want to normalize, you keep it like this. And it happens that this normalization has a physical meaning on top of that, which is a happy thing.
my point being asking in this is that the entire, especially the non-trivial things that we find in quantum information theory, such as entangled states or any other such these non-trivial properties, are in a space where density matrices play out. So why this definition is not like for example, when you wrote down the postulates, a situation has its corresponding state in the Hilbert space. That in that definition, density matrix, yeah, we write the state has also something called a density matrix.
Yes.
There's like direct correspondence, like that you can go from one to another, like a situation to a density matrix.
Yes.
So where did this come up? What context density matrices are a space where a Hilbert space of bound operators? Where did this come up? And why did this come up?
I'm not getting the question. I mean, you want to question why we use density matrices for situations?
I think he's asking why we use Hilbert spaces to describe physical systems.
No, that is a much bigger question. I want to know in Hilbert spaces why density matrices have a correspondence to the physical system.
So the point is that, I mean, I don't know how to answer it in the perfect way, but one way you can think of it is the spectral theorem. Is that you consider orthogonal states, A and B, let's say. So these corresponds to distinguishable situations, and so these are orthogonal vectors. And then we know that in reality there can appear situations where I have prepared this or this I have forgotten, and I have a measure of how much I have forgotten, and so this gives me these probabilities. I want to mix them, and then you mix them. If you write it in this way, then it gives you the connection with the probability and the Born rule very easily. It's just a handy way to, you can forget about density operators and think only in terms of ensembles. That will not hurt you, except you have to remember that the density matrix that is created from that ensemble is blind to the which decomposition you have used to create it. By the way, this whether the description of a situation by a density matrix is the correct one is now being questioned by people, and there are quite a few papers, notably one by Popescu, where they question whether a situation can always be described by that. So actually the last paper maybe you have.
Isn't this again Reason's theorem?
Pardon?
Isn't this again Reason's theorem? You have to get a probability in that way, then the density matrix is an essential thing.
Maybe, I don't know.
What is this theorem, Mr. Mark?
This is what I don't know. I'll tell you next week. I really forgot the connection of the Huygens theorem with bond rule. It's a way to say that the bond rule is the only option that you have.
Ah. Oh.
But again, it's not a proof, okay? Some intuition. There are other people who have done, so Zurek, for example, has a way of deriving within inverted comma the bond rule under certain assumptions, of course.
So what you're saying, Popescu is questioning that.
Yeah. So if you see I think it's the last paper of Popescu. It's about a year old maybe, or maybe 6 months old, and he's questioning whether the density matrix gives. So current belief is that the density matrix gives the complete representation of a physical situation. So he cooked up a physical situation where it's not the case. And we have had discussions in the group with many people, and we sort of looked at it very carefully. We couldn't find any mistake. So, and Popescu is a learned person.
So is it challenging the arbitrariness of the measurement outcome?
No, so it's challenging the very postulate that every situation, so he has cooked up a physical situation which you cannot describe by a density matrix. You assume that you can describe, and then you land in a paradox. So actually is very interesting. He cooks up so he says that somebody has a laboratory, and somebody else comes and says that this is my laboratory, and he wants to go and prove it in a court of law, but he believes in quantum mechanics, so he uses the density matrix to represent the states that is created in the laboratory, and he loses the case.
Quantum mechanics cannot totally describe a universe. The title is something like that.
I forgot the title. So actually, this Sudhir, who is a visitor to our group from IISER Pune, he works in this.
So
That has to do something with hidden variables.
It's not clear.
the assumption also in basic quantum mechanics, we also assume that the Hamiltonian is a Hermitian operator. All the observables are Hermitian operators. But
Yes, I mean, in the way that we are describing quantum mechanics, the observable doesn't even appear. I mean, I can tell you how the observable comes.
yeah,
It is just a bookkeeping apparatus.
that is fine. But in the start, at least we assume that it's a Hermitian observable because we need real eigenvalues and real observables, and therefore it gives rise to unitary dynamics. People also study non-unitary dynamics with a non-Hermitian Hamiltonian but with real eigenvalues.
Oh, so you're talking about the PT symmetric case, or
Something like that.
so that is a different scenario that I don't know very much.
But
a non-unitary dynamics can appear in a different way also. That if you have a two-particle system or many-particle system, where you have a unitary evolution of the whole thing, but you are looking only at a part of the system, it will appear as a
because
non-unitary.
it cannot be broken down into many unitary operations of
Exactly.
single particles. But that still is governed by a whole Hamiltonian.
That is, the
Which
entire
is
thing is
Hermitian.
unitary operator.
So people study that, or people
Study that. So this is so in our group a lot of people study that in open quantum dynamics. So it's the Breuer-Petrucciani book. So, but yeah, there is this PT symmetric thing that I don't know much about it. It's related to the measurement problem and many other things. I don't know. Okay. Anything else?
Quantum states and knowledge, that is a paper.
Could be. Is that the last paper?
30 November 2018.
2018. Okay.
Signed Popescu.
state them.
This I showed you.
No, it's not even not published as
Not
yet.
published.
It's not yet published.